last class, I told you about the advantages and disadvantages of negative feedback. In this class, I am going to explain in detail about the advantages of negative feedback. Advantages of negative feedback in amplifiers. The last class I mentioned there are mainly 4 advantages due to the negative feedback. The first advantage is stability in gain. Okay. I'll explain the stability in gain concept in detail. Yes, the gain with feedback. For negative feedback, the gain with feedback AF is equal to A by 1 plus A beta. Okay. Now, differentiate this total expression with respect to A. Yes. If you differentiate the total expression with respect to A, you are going to get 1 by 1 plus A beta whole square. Okay. Now, just take dAF is equal to dA into 1 by 1 plus A beta whole square. Now, divide the total equation with AF. That is, dAF by AF is equal to dA by AF into 1 by 1 plus A beta whole square. Okay. Yes, that is dAF by AF is equal to, yes, dA into 1 by 1 plus A beta whole square. Here in the denominator you have AF. AF is equal to A by 1 plus A beta. As this is in denominator, you will get 1 plus A beta by A. Okay. So now, cancel these two. So you will get dA by A into 1 by 1 plus A beta. What is this? dAF by AF is equal to dA by A into 1 by 1 plus A beta. Okay. What is dAF by AF? It is the fractional change in gain with feedback. Okay. And what is dA by A? The same, fractional change in gain without feedback. Okay. So now you've observed the expression is the fractional change in gain with the feedback is lesser than the fractional change in gain without feedback by 1 by 1 plus A beta times. Okay, we all know the denominator of this 1 by 1 plus A beta, that is 1 plus A beta is always greater than 1. So what is 1 by 1 plus A beta? Always less than 1. Means, yes, dA by A is multiplied with a value which is less than 1. So totally what will happen? dAF by AF becomes less. Okay, so the fractional change in gain with the feedback is lesser than fractional change in gain without feedback. Means there exists stability if you use a negative feedback in the case of amplifier. Because what is this? This is fractional change in gain. Yes, change in gain is less. Means V0 and Vi are stable. Then only the gain change is less. If V0 and Vi are stable, you can say the amplifier is a stable amplifier. So with this expression, we can say that yes, there exists stability in gain if you use a negative feedback in amplifier. Okay. So here is a factor called sensitivity. Sensitivity S is equal to dAF by AF by dA by A. Yes, what is this? 1 by 1 plus A beta. Okay, so this term is called sensitivity term, and there exists opposite term called desensitivity. Desensitivity D equal to 1 by S, that is 1 plus A beta. Okay, yes, so this is about the stability in gain. Okay, means yes. So in terms of desensitivity, we can say that the fractional change in gain with feedback is lesser than the fractional change in gain without feedback by a factor desensitivity. Okay, so with this we can say there exists stability in gain if we use a negative feedback in amplifiers. Okay, now I'll explain the second point. Increases the bandwidth if you use the negative feedback in amplifiers. Okay, so what is the second point? Increases the bandwidth. Yes, so what is the bandwidth? Now I'll explain in a simple way about the bandwidth and the frequency response. Yes. In general, for an amplifier that we are using for audio frequency purpose, the frequency response is like this. Okay. And if you take this as gain in dB, this acts as gain in dB. What is this? This is your frequency response. Okay. This is your maximum gain. And yes, by subtracting 3 dB, this is your 3 dB. Draw a line. It touches the response at 2 points. This point is called, upper cutoff frequency, and this is called lower cutoff frequency. So what is bandwidth? FH minus FL. Okay. So this is the frequency response of a simple amplifier which is not having any feedback. Okay. Now for this type of amplifier, if you apply negative feedback, what will happen? The bandwidth is going to be increased. That I want to prove. Okay. So now, yes, we know AF is equal to A by 1 plus A beta. Yes. Now, see the frequency response. It has 3 regions. This is the lower frequency region, and this is the higher frequency region, and this is the mid frequency region. This equation AF is equal to A by 1 plus A beta holds good for any region. Means you can apply the same formula even for low frequencies, high frequencies, and also for mid frequencies. Now I am writing the same expression for all the 3 frequency regions. Okay? Yes, it is AF low. Means for low frequency region, it is A low by 1 plus A low beta. And for high frequencies, AF high is equal to A high by 1 plus A high beta. And for mid frequencies, AF mid is equal to A mid by 1 plus A mid beta. Okay. Yes, these are the 3 equations. Yes, for low frequency, high frequency and mid frequency. By using these 3 frequencies, we are going to see what is happening to the bandwidth if you apply a negative feedback. Okay, yes. So see here, a bandwidth is FH minus FL, upper cutoff frequency minus lower cutoff frequency. Now with the application of negative feedback, there exists changes for higher cutoff frequency and lower cutoff frequency. Okay. So now I'll explain what is the effect of negative feedback on lower cutoff frequency, and then I'll explain what is the effect of negative feedback on higher cutoff frequency, so that we are going to get the effect on bandwidth totally. Okay. So let me start. Effect of negative feedback on lower cutoff frequency. negative feedback on lower cutoff frequency. Okay, there exists a relation between the gain at low frequency and the gain at mid frequency. It is already a derived equation. That is, yes, A low by A mid. Okay, A low by A mid is equal to 1 by 1 minus J FL by F. Okay. A low is the gain at low frequencies and A mid gain at mid-range frequencies. FL is lower cutoff frequency and F is the applied frequency. This is for amplifier without having any feedback. So, what is this expression? It gives you A low is equal to A mid by 1 minus J FL by F. Okay. So, take the equation numbers 1, 2 and 3. Now it has 4. Okay. Now, substitute equation number 4, see here, in 1. Okay. Substitute 4 in 1. It implies, yes, AF low is equal to, yes, here is A low. So, A mid by 1 minus J FL by F by, see here, 1 plus A low beta. So, 1 plus A mid by 1 minus J FL by F, yes, into beta. Okay, yes, now just take the simplification. Yes, you're going to get A mid by, yes, this is take LCM and now you get 1 minus J FL by F plus A mid beta. Okay, now divide this numerator and denominator with 1 plus A mid beta. So, you're going to get AF low is equal to A mid by 1 plus A mid beta by, yes, here is 1 plus A mid beta, so you get 1 minus J FL, yes, as you're dividing with 1 plus A mid beta, you're going to get F into 1 plus A mid beta. Okay, yes, so now you can write it as A mid by 1 plus A mid beta divided by 1 minus J FL by F. FL by F. See, what is A mid by 1 plus A mid beta? See here. Equation number 3. A mid by 1 plus A mid beta is nothing but AF mid. So, totally it is AF low is equal to AF mid by 1 minus J FL by F by F. Okay. Yes. Where your FLF is equal to where your FLF is equal to FL by 1 plus A mid beta. Okay. Okay. So what happened to the frequency? See, I already told you, FL is the lower cutoff frequency in the absence of negative feedback. FLF is lower cutoff frequency when you apply a negative feedback. So what is happening here? See here, FLF is equal to FL by 1 plus A mid beta means the lower cutoff frequency is decreasing by 1 plus A mid beta times when you apply a negative feedback for your amplifier circuit. Okay. So, remember this point, FLF is equal to FL by 1 plus A mid beta. So, this is the effect of, see here, effect of negative feedback on lower cutoff frequency. Okay. So, the lower cutoff frequency is decreasing. Means, if it is FL, then your FLF is decreasing. Means, your FLF goes like this. It is nearer to 0. Okay. So, now I will explain effect on higher cutoff frequency. Okay. Okay, so now it is effect of negative feedback on higher cutoff frequency. Okay. So what is the higher cutoff frequency without feedback? It is FH. Now we are going to derive the upper cutoff frequency or the higher cutoff frequency when you apply a negative feedback. Okay. So let's just a relation between the gain at high frequencies and gain at mid-band frequencies. Similar to the relation between gain at low frequencies and gain at mid-band frequencies, here also there is a relation between gain at high frequencies and gain at mid-band frequencies. That is A high by A mid is equal to 1 by 1 minus J F by Fh. Okay, so this is the existing relation, we are using it. So what is this? Now you will get A high is equal to A mid by 1 minus J F by Fh. Okay, now take this as is, I think it is, let it be equation number 5, I think 6. Let be equation number 5, this derived relation as equation number 5. Now it becomes the equation 6. Now, substitute 6 in 2. Okay, so implies AF high, see the equation number 2. AF high is equal to, A high is A mid by 1 minus J F by Fh by, and see 1 plus A high beta. So 1 plus A mid by 1 minus J F by Fh into beta. Okay. So in a similar way, take a cancellation and take LCM. Yes, you are going to get A mid by, yes, 1 plus A mid beta minus J F by Fh. Okay. So now also you divide the numerator and denominator with 1 plus A mid beta. So you are going to get A mid by 1 plus A mid beta divided by, again 1 plus A mid beta by 1 plus A mid beta will give 1. Okay. So 1 minus J F by Fh of 1 plus A mid beta. Okay. Then what is this? See here. A mid by 1 plus A mid beta is AF mid. Okay. So it is AF mid by, yes, 1 minus J F by Fh F. Okay. Yes. What is FHF? FHF is Fh of 1 plus A mid beta. Okay. Yes. AF high and this is equal to AF mid by 1 minus J F by FHF. Okay. Okay. Actually, we started with A high by A mid, means without negative feedback. Yes, we got the relation with the feedback. Okay. So in that relation, the frequency, upper cutoff frequency Fh gets multiplied by 1 plus A mid beta. Okay. So now if you observe these two expressions, equation number 5 and equation number 6. If you see equation number 6, FH is the upper cutoff frequency without negative feedback and FHF is the upper cutoff frequency with negative feedback. What is happening? It gets multiplied with 1 plus A mid beta, means the upper cutoff frequency is increased. Okay. So here the lower cutoff frequency is decreased. Okay. So with the negative feedback, totally lower cutoff frequency, see here, lower cutoff frequency is decreased and upper cutoff frequency is increased. Okay. So if you write that, then yes, another point is, we know the gain decreases with the negative feedback. We already know it. So how is the response now? See, this is the response. This is without feedback and this is with the feedback. Yes. Now this is your FHF and this is FLF. FHF and FLF. See this. Yes. So what is happening to the bandwidth? The bandwidth BWF is equal to FHF minus FLF. So what is happening? So in the initial case, what is the bandwidth? Up to this is your bandwidth. This is your bandwidth. But when you apply negative feedback, the bandwidth becomes like this. So this is increased to this amount. So with the negative feedback, bandwidth increases. Okay, so this is the derivation about the increases in bandwidth if you apply a negative feedback. Okay. Okay, then the third point is decreases the noise and distortion. Okay. Decreases the noise and distortion. Yes, what is noise and what is distortion? Suppose if your signal consists of some noise, then there is no change in shape of our signal. The characteristics of the signal may change. Okay, means extra signals may overlap with our signal, but there is no shape change. But if distortion is added to our signal, then automatically the shape of the signal is changed. But with the application of negative feedback for our amplifier, the noise and distortion gets reduced. Because see here, yes, we know with the negative feedback gain decreases, we know. Because loop by loop, the feedback voltage is decreasing from the source voltage. We know it. Vi is equal to Vs minus Vf. Okay. In the same way, if a noise is presented in the amplifier, then it comes out as output of the amplifier and that gets connected back to the input and it gets subtracted from Vs. So what is happening? Loop by loop, the noise signal voltage is decreasing. Loop by loop, the distortion related signal voltage is decreasing. So what is happening with the negative feedback? Yes, noise and distortion gets reduced with the negative feedback loop by loop. There is a simple concept here. Suppose without feedback, noise is N, and with the feedback, noise is NF. So what is NF? NF is N by 1 plus A beta. It gets decreased by 1 plus A beta. In the similar way, suppose without feedback, distortion is D, and with the feedback, distortion is DF, then DF is equal to D by 1 plus A beta. Okay. Yes, just keep in mind, noise and distortion are added like voltages, signal voltages, okay, like signals. So we know the gain decreases because output voltage is always subtracting from Vs. In the same way, the noise related output or the distortion related output is also continuously subtracted from Vs. That is the reason continuously noise and distortion gets reduced. Okay. So the fourth point is, what is the fourth point? Modifies the input and output impedances. Okay. Yes, this negative feedback modifies the input and output impedances of the feedback amplifier. Okay. So this is a big concept. We must define the types of feedback amplifiers and we have to draw the feedback amplifiers equivalents. Okay, this is a big topic. So in the next class, I will cover this concept, how the negative feedback modifies the input and output impedances. Okay, thank you very much. If you like this lecture, please don't forget to like, share and subscribe. Please support the channel and please share this information with your friends. Okay, thank you very much.
Thank you for watching this video. If you like this video, please don't forget to like, share and subscribe.